Take a look at your GPS map. Then look at a family ancestry chart. Then look at a conversation with ChatGPT. How exactly does a computer organize physical geography, human genetics, and human language all at the same time? Underneath the interface, these experiences are built on the same architecture. They are a simple arrangement of dots connected by lines. These connections form the common language that allows software to navigate a city, trace a lineage, and process a sentence. The easiest way to see this architecture is to look at a basic city street grid. When you strip away buildings and terrain, you're left with a series of street corners. In computer science, those intersection points are called nodes. The roads linking those corners together are called edges. Put your nodes and edges together and you get a graph. Every map application relies on this mathematical structure to calculate where you are and where you can go. For a raw graph to be useful, it has to reflect the constraints of the real world, starting with traffic flow. A mutual friendship on Facebook is a two-way street. Following someone on Instagram who doesn't follow you back is a one-way street. When we draw arrows on the edges to show which way the data can move, we create a directed graph. But traveling down a real road carries a cost. It takes 10 minutes, or it spans 5 miles, or it has heavy traffic. We represent that cost by assigning numerical values to the edges. Now our map is a weighted graph. Watch how the routing algorithm works here. It explores the possible paths from point A to point B, adds up the weights along each route, and selects the one with the lowest total. That math is called pathfinding. It calculates your morning commute, aggregates the cheapest international flights, and plans the next move in a chess engine. You can take that highly connected graph and force it into a rigid hierarchy by imposing 2 strict rules. Rule 1. Information can only flow one way, down, like a parent passing traits to a child. You never reverse upward. Rule 2. Absolutely no loops. A data point cannot link back to its own ancestors. You can't be your own grandparent. Apply those 2 rules, and your graph becomes a tree data structure. As a quick quirk of computer science, these trees grow upside down. The single starting point at the top is the root. The dead ends at the very bottom, the nodes with no further outward connections, are the leaves. A tree is simply a graph that surrendered its ability to loop in exchange for perfect organization. You can distinguish a graph from a tree by checking for a single property. Can you walk along the lines in a circle and end up where you started? If loops are possible, it's a graph. If there is only one starting point and no way back up, it's a tree. This comparison shows your standard computer folder directory on the left and its exact mathematical equivalent drawn as a tree on the right. You see the same structure in reply threads under a social media comment. Anytime digital information nests neatly inside other information, a tree structure is quietly running the software. To summarize how these concepts link the physical world to digital code, street corners are nodes, roads are edges, costs are weights, and a system with no loops is a tree. Look at this command line interface. By typing the word tree, your computer will instantly map out the true shape of your hard drive in plain text. It's a physical data structure living on your machine. Now, consider what happens if the edges on a weighted graph could autonomously learn. As digital traffic passes through, the graph adjusts its own weights, strengthening some roads and weakening others. A graph that adjusts its own weights until it teaches itself to recognize patterns is a neural network. It is the foundation of artificial intelligence, and it's what we'll build in the next video.